This video, in case you hadn't guessed, is about probability plots. So before we get into the esoteric mathematics behind these, we might just pull up a probability plot. Let's say that we have a normal curve like this one, and we wanted to check it against another normal curve. Now, wouldn't you expect that these two are identical? So if we plotted the same 5 points here, like equidistant from the center Z, on each of these, it should end up being a straight line here. So let's try it. Now the thing is, if I pick 5 points here, like I'm going to do that exactly right now. See, it's n is equal to 5, so I'm going to check 5 points. Now it picks it randomly, so it's obviously got 2 right here where this thick line is. Okay, so we've got 2 right here, and right here we've got 2, the first 2, the third, fourth, and fifth. So 1, 2, 3, 4, 5. You can see these were randomly selected. So it should be a straight line, but it's actually not quite. You can see it's a little bit funny. Let's try generating another 5 points. Okay, there we go. Now it's a line, but again it's a little bit off. Let's see if we can generate randomly 5 that look sort of like the 5 on this side here. I'm trying, see how it's changing as it's, okay, come on, get something that looks sort of, okay, that one looks a little bit close to this kind of design. So so you can see it looks pretty linear, right? We're taking the first point of each one and taking its height, and the height, if it was exactly the same on each one, the heights would be the same, and so of course as far as we would go along this axis would be identical to how far we went along on this axis. Let's try increasing our n. So we're going for, oops, that's our m. I don't want to increase that, so let's put it back. Get back there. Come on. Stop that. Okay, there we go. We want to increase n. So now we've got n is equal to 20. So it'll be a little easier now to get randomly points that actually, you can see that it looks much more linear, right? Because the first point and the first point, second point, and so forth, it goes along and it looks pretty linear. Let's try, oh, we're going to go all the way. We're going to go up to 100. Now, as you might imagine, it's going to look pretty darn linear, this correlation plot, and it does. Even when let's see, I'm going to do it a bunch of times, and you can tell it looks pretty linear. So this is the main idea of what we're going to be doing in this tutorial today. So what's it all about? You've just sort of seen it, but in essence, it's often important to determine the type of distribution for a random process. A probability plot is the way we can see what type of process we might have. For example, before we were comparing a normal curve to a normal curve. What if we compared a normal curve to a uniform curve? Well, a major thing we could expect is that it's not going to be a linear comparison. Let's take our n back up. We're going to take it up to 100. Okay, now we're going to compare these two, and what we should see is something completely nonlinear. Well, that looks pretty nonlinear to me. Let's try again. There's another one. In fact, I think we can actually make it so let's see, it's going to continuous. So I'm going to let it run. Come here, you're supposed to be continuous. Oh, maybe that'll do it. No, it's not doing it. Oh well. You can get the idea though. It's not very linear for the most part. So let's try now. Oh, well, now it's off doing its thing. You can see. Oh, it's probably slow to update because I'm doing so many. Let's try gamma distribution. Here's a gamma. We're going to compare. Go for it. Okay, you can see it sure doesn't look linear. So the best way for us to compare, to figure out what a distribution is sometimes, is to just take our regular distribution and compare it to the other distribution and see how linear it is. See, let's do that by, now we're going to take a uniform on the right, and let's just take it up to 20 or 15. Okay, that's fine. And we'll compare it against a normal, and it's like really bizarrely nonlinear. But now let's compare it with a uniform. Here we go. Well, that doesn't look so good, but it's kind of linear, roughly. Let's get a, let's go up to 50. Okay. Well, now it is looking pretty linear. So, but if we tried comparing uniform to exponential, it looks bizarre. So, again, that's how we can compare and find out what kind of underlying distribution we might have. So this is really easy. It's just putting it into words that makes it seem more difficult than it actually is. We say the pth percentile is a value, y of p, such that at most 100p% of the measurements are less than this value, and 100 times 1 minus p% are greater. The 50th percentile is called the median. So we're going to show you an example of this. It's really straightforward. The sample 100p percentile, or p quartile, is that data value such that 100 times p% of the data are less than or equal to it, and 100 times 1 minus p are greater than or equal to it. The sample 25th percentile is called the first quartile, and the sample 50th percentile is called the sample median, or the second quartile. Sample 75 percentile is called the third quartile. So everything just as you expect. The 100th percentile of a continuous distribution with a cumulative distribution function f of x is the number x such that this f of this function h of p is equal to p. Okay, now the best way to think of this value right here is, and it's not always true, it's only true for normal distributions, but it's like this is the z value, the z-score, and this is the area affiliated with that z-score, right? Which is obviously the percentile, or the percentage. For example, the 63rd percentile, h of 0.63, satisfies that this area is 0.63. So you can see it's like f of this, well, I'll say z value, although it can apply as well for non-normal curves, is equal to 0.63. So that means 63% of the population lies below this eta 0.63, and 37% lies above that eta, which is the same as the h, 0.63. Okay, so if we wanted to, for example, determine the 72nd percentile for the standard normal distribution, well, this is pretty close to 72nd percentile, right? So it's going to be right around here. And if that's the case, it's going to be at a z value of, well, let's see, 0.58. Z is equal to 0.58. So if we go back, this right here, this h of, well, let's see, what were we at? We were at 72nd percentile. So h of the 0.72, or that can be h or eta of 0.72, is just going to be equal to 0.58. Okay, now don't worry. We're going to pursue this, and it's going to make more sense as we get a little further along. So, consider a random sample. We've got n measurements, however many n, let's say 100, from a random process. If we arrange them from the smallest to the largest, then the ith measurement, like the first one, the second one, or whatever, is going to be 100 times I minus 0.5 over n. So, for example, if n is 10 samples, if we have 10 samples, then we would define the I different measurements, right, the ith measurements as, well, first I is 1, so that gives us 5%, then I is 2, gives us 15%, all the way up to 95%. This is the way we just simply break down all of the 10 different samples. So, for example, we would just draw a Gaussian curve, and it would be something like 5%, 15%, 20%, and so forth, all the way. I'm not drawing it very well, but that's how we would divvy it out to try and get 10 different samples. That's just the mechanics behind how we would do that. So a probability plot is that two-dimensional plot that has n points, and that's just exactly the plot that I was showing you earlier, right, where it's going to be something, well, that's not very well done, but you get the idea. The plot is used to determine the probability distribution for the random process. Each point consists of the following pair. On the x-axis, we have the proposed distribution, and then on the y-axis, right, so we're thinking it's normal, and then this is the comparison, the first point of comparison for the sample. So, how do we construct a probability plot? So, we just constructed them quite easily by using that one simulation, but if we're actually doing it mechanically ourselves, what you would do is first select whatever sample size you're going to have. Are you going to take 5 points, 20 points, 100 points, or whatever? Okay, so what I'm going to do is, let's skip ahead a little bit. So there's the sample percentages. Notice how they're calculated using this formula. So in this case we had 10 samples, so it ends up being 5, 15, and so forth. So we've calculated the sample percentages. Now choose your proposed probability distribution for the random process, and you calculate its n percentiles. So I'm going to skip ahead just a little bit here so you can see what I mean. Okay, there's the sample percentages. Now here's your percentiles. This value right here, that is the z-value for a normal distribution if we were using that. So look, 95%, it's exactly where you would expect. So z is equal to 1.65. Here's, well, you can see 50% would fall at 0, and at 5% it's at a z-value of minus 1.65. So basically we're just correlating or putting into a table the fifth percentage point right here is at 1.65, and there. So anyway, that was the choose the proposed probability distribution, and then write down the z-value if it is the normal curve. Then collect a sample of n independent measurements from the random process and place this data into the table where each row contains the data arranged from the smallest to largest values. Okay, so let's pop back ahead. So what I've done is I've taken, here's the fifth percentage point, and that's got a z-value that corresponds to minus 1.65. The actual measurement for that first point was minus 1.90, and 15, and so forth. So now I'm going to step back again, and basically I've just walked you through how you set up the measurements in your table, and then you'll plot those measurements, sort of in essence, the z-value, if it's the normal curve, versus the measurements, And you're going to be doing exactly what I showed you at the beginning of this video. So if we evaluating a probability plot, if the random process has the same distribution as the proposed one, then the percentiles and the measurements defining each point should be reasonably close. So in other words, the probability plot will fall close to a slope of +1. And we've already visualized that a bit. But if the points don't line up near this line, then the random process might not have the proposed distribution. And we saw that. So for an example, we have, let's say we have 10 independent measurements of a random variable that we've gotten from a random process. We've got, here they are, and we're asked to construct probability plots to determine whether this random variable has a uniform distribution with these limits on it, or a standard normal distribution. So first thing we do, we say if it has a uniform distribution, we've first got to calculate those n equal 10 sample percentages. So there we go, it's 5, 15, and so forth. We just plug into that formula. And then we're going to calculate the n equal 10 percentiles. So this is kind of like the z-score, right? But so in this case, though, it's a uniform distribution. So that means that we're going to have, like, the 5th percentile. Let's see, this starts at, let's see, they said 2.2, oh, minus 2.2 to plus 2.2. So we're actually going to have it ranging between minus 2.2 and plus 2.2. So that means first, now, however much area we've got here, we need 5% right here. So sort of the z coordinate, kind of that 5% is obviously going to be somewhere around, I don't know, around minus 2. And indeed, if you plug into the actual equation, you find that the value you're looking for 5%, and pause this, take a look at this equation and see how it's obtained, right? This is actually the cumulative distribution function for the uniform distribution. So they plugged it all in, they've rearranged it, now they're finding the value where there's 5% of distribution is less than that particular value. And that turns out to be minus 1.98. So I was pretty close when I said 2. And likewise, you just keep plugging in 25%, and then you find your eta p value and so forth. So you keep doing that. You create your table. And then what you do is you compare, for each point at that 5%, theoretically it should be minus 1.98. So then you compare that with the actual first measurement and so forth. So you're comparing everything all the way along. You plot the percentiles versus the measurements, right? So here's sort of the x coordinate, here's the y. So this one, remember, is randomly generated. So even if it is the proper distribution, it may not show up as having a good line. But there we go. Here's the comparison, the x and y, and what we see is something of a poor fit. It's a series of consecutive points that lie above or below the slope of the +1 line. So uniform distribution doesn't seem to be maybe appropriate for that particular sample distribution that we had obtained. So let's compare it with the standard normal distribution. And we'd already snuck ahead and peeked at this thing. We calculate our different percentile points, and then we calculate the eta p values for those particular points. And this time we're using of course, a standard normal distribution. So when we find the z value, it actually is the z value, right, that you see here. And then we say place the measurement points against those. So the first measurement point is corresponding to the eta of p value, which is the z value of minus 1.65. And we go all the way through, so we have this nice table, and this is our x value right here, x value, y value, and we plot those all the way up and we see how it looks. And what we see is a better fit. We have approximately the same number of points scattered on both sides of the line. So that's kind of nice. Later in the next course we would learn about regression analysis, and that would help you determine how well that line actually fits the data. So what if you think the random process has a normal distribution but you don't know the mean or the standard deviation? Well, if you recall, a percentile eta of p from the standard normal distribution can be linearly transformed to any normal distribution. That is, this is just a rewrite of our usual equation. Z is equal to x minus mu over sigma, and this is just rearranged. And remember that if we take a look at our usual equation right here, we can rewrite that in this form, and this f of z eta of p is actually like a z value, and this one of course is like an x value. So we can construct a probability plot using the percentiles eta p from the standard normal distribution, and if the random variable has a normal distribution, the points will lie on a reasonably close to a straight line with a slope of the standard deviation. Pretty cool, huh? That's it. Standard deviation and a y-axis intercept of the mean. Slick, huh? So let's say, for example, it's believed that the amount of time to place a phone order for a pizza is normally distributed. The time in minutes to complete the 16 randomly selected calls are given below. We're supposed to construct a probability plot to estimate the mean and the standard deviation. So we can do that, right? We can figure out if we've got 16, we construct our coordinates there and the eta of p value. And remember, this is related to a z characteristic because we're saying it's a normal distribution. Here's our times, and we go ahead and plot things out, and you can see sort of, kind of, it seems to work, be kind of linear. And all you have to do, and I'll leave this for you, is to calculate out the y-axis intercept, and that's the mean. And of course the slope itself is the standard deviation.